The written history of naval warfare is frequently dictated by institutional momentum rather than physical evidence. On July 30th, 1942, a German submarine designated U-166 was hunting in the Gulf of Mexico. This Type 9C boat was the only vessel of its kind to be destroyed in this specific theater of operations. Over the course of its short operational life, the submarine had sent 4 Allied merchant vessels totaling just under 8,000 gross registered tons to the ocean floor. Its final action was the successful torpedoing of a large passenger steamer. Instantly following that sudden strike, a United States Navy submarine chaser designated PSC 566 moved to intercept. Directed by its commanding officer, the small escort vessel executed a rapid, localized depth charge attack over the last known position of the enemy boat. The surface crew carefully observed heavy oil and shattered structural debris rising to the surface of the water. Relying on this visual confirmation, the commander filed a formal tactical report claiming a fatal strike and the total destruction of the enemy vessel. The institutional response from Naval High Command was immediate and dismissive, allowing high-level assumptions to override frontline tactical evidence. The reviewing officers concluded that an inexperienced surface crew on a minor escort vessel lacked the operational proficiency to sink an active enemy submarine on their first attempt. They officially rejected the physical observations of oil and debris, ruling them inconclusive. The commanding officer was summarily removed from his ship, formally reprimanded, and transferred to a remedial anti-submarine warfare training school. His accurate tactical report was effectively erased from the permanent combat record. Just 2 days later, a Coast Guard aviation crew operating in the same broad geographic region dropped high explosives on a completely different submarine. That second engagement occurred over 100 miles away from the original surface attack coordinates. Despite the vast geographical discrepancy and the absence of the same kind of wreckage confirmation, record keepers accepted the aircraft engagement as the official explanation. The naval authorities credited the aviation crew with sinking the submarine, closing the active file. The accepted record left the surface commander professionally disgraced and the actual engagement coordinates ignored. Correcting this massive institutional error would eventually become a primary historical objective. Future investigators needed to positively identify the true sinking location to resolve the evidence dispute, match the combat logs, and properly restore the official military record. However, achieving this vital objective required operating under incredibly severe jurisdictional constraints. This undertaking could never function as a standard marine salvage operation. When the hostile submarine finally went down, all 52 crew members were lost with the boat. Their deaths made the wreck a protected war grave, placing legal and ethical controls around any future work and creating a presumption against disturbance. Commercial salvers and engineering teams could not treat the wreck as recoverable property, and any proposal to attach lifting cables, cut through the steel casing, or remove interior artifacts would require extraordinary authorization that was incompatible with the archaeological approach used to identify the boat. The definitive evidence required to overturn the Naval High Command ruling was trapped inside a sealed tomb, and that tomb was permanently off limits to physical intrusion. Any authorized attempt to gather forensic proof would therefore have to be conducted primarily from outside the wreck. Investigators would rely on remote sensing, exterior visual documentation, and only tightly controlled scientific sampling, if specifically permitted under the site's protection rules. The entire historical proof chain rested on the fundamental assumption that the visible structural damage on the outside of the submarine would be distinct enough to match the original depth charge attack logs. If the disgraced surface commander had been accurate in his initial combat assessment, the shattered steel evidence had to rest exactly where he claimed, waiting patiently for a technological era capable of reaching it. Any search for physical evidence was immediately halted by the fundamental sensor limits governing the deep ocean. Confirming the true location of the sunken submarine required overcoming an absolute environmental barrier in the Gulf of Mexico. The target rested far beyond the reach of standard recovery operations at a staggering depth of 5,000 feet. At this extreme depth, the physical characteristics of the water column completely alter the operational landscape. The environment is entirely devoid of natural light, rendering traditional optical search methods useless. More critically, the hydrostatic pressure at 5,000 feet demands equipment built and rated for deep ocean work. Human intervention is biologically impossible at that depth without specialized submersible systems, and shallow water camera housings or unrated electronics would fail under the strain. Surface-based sonar can reveal broad seabed anomalies, but at this depth, the decisive images required sensors flown close to the bottom. High-frequency side-scan sonar mounted on a deep-rated vehicle could pass just above the mudline and preserve the resolution needed to separate a submarine hull from the surrounding sediment. The immense vertical distance did not make detection impossible. It made casual detection unreliable. The hostility of the environment extended far beyond the simple mechanics of vertical descent. The geographical location of the sinking site introduced a secondary, equally formidable layer of protection. The target area lies within the geological formation known as the Mississippi Canyon. The seabed in this deep water sector is dominated by fine silt and clay rather than hard exposed rock. Over thousands of years, river-borne particulate matter has settled across the canyon floor, creating soft sediment that can embed heavy wreckage, resettle around it, and mute visual evidence. At the site itself, the stern and main hull section sits largely upright on the canyon floor, with silt rising against the flanks and in places nearly to deck level. Because site protections prohibit dredging or excavation during archaeological survey, the lower pressure hull and keel remain hidden from direct observation. The bow section, however, is a separate wreck component lying apart and partly embedded on its side. Defeating this dual defense of depth and burial required immense technological patience. The site kept its true identity hidden for decades. Sonar contacts in 1986 revealed 2 targets, but the smaller wreck was not correctly identified as the submarine until 2001. When commercial high-resolution acoustic mapping finally revisited the area, it produced a definitive and disruptive result. The acoustic mapping stripped away the first layer of environmental denial without yet resolving the target's identity. However, sensing an anomaly through a mile of water is entirely different from capturing verifiable visual evidence. Bypassing the remaining barrier required specialized acoustic robotics originally developed for deep water industry, not wartime archaeology. That opportunity arrived through the offshore energy sector, which in 2001 was expanding infrastructure across the deep water Gulf of Mexico. Laying hundreds of miles of commercial natural gas pipeline across the ocean floor requires absolute geographical precision and intense risk management. The governing engineering mandate for this type of operation is strict obstacle avoidance. Project managers and marine engineering teams had to ensure that the proposed commercial pipeline route was completely free of geological hazards, discarded industrial debris, or undocumented maritime wrecks. Striking a massive steel structure during the automated pipe-laying process would cause catastrophic damage to the extremely expensive commercial infrastructure. To clear the proposed route, commercial marine surveyors deployed a highly specialized technological asset. They utilized an autonomous underwater vehicle. The untethered platform could run a precise pre-programmed grid just above the mudline using high-frequency side-scan sonar while avoiding the cable and tether limits of traditional oceanographic gear. The vehicle sent rapid acoustic pulses outward through the dense water column, precisely measuring the time it took for the returning echoes to bounce back to the sensor array. While the soft canyon sediment absorbed much of the acoustic energy, hard metallic surfaces reflected the sound waves sharply back to the robotic platform. During a routine acoustic sweep of a deep canyon sector, the autonomous vehicle detected a massive, rigid obstruction near the proposed pipeline route. The distinct acoustic shadow cast by the anomaly indicated a massive artificial structure standing proud of the surrounding sediment. By cross-referencing the geographic data logged by the autonomous vehicle with the known wrecks and wartime records, researchers realized something profound. The sonar anomaly lay near the passenger steamer SS Robert E. Lee and roughly 140 miles from the aircraft attack location that had long received official credit. This acoustic mapping placed a substantial wreck where the initial surface action made historical sense, not where the later aviation claim required it to be. Despite this incredible geographical match, the operational parameters of the commercial survey imposed a strict boundary on any immediate follow-up action. The rigid pipeline clearance objectives dictated the initial scope of the deep water investigation. The commercial survey team was funded exclusively to map potential hazards and route their energy infrastructure safely around the newly discovered obstacle. They were not authorized, equipped, or permitted to conduct a comprehensive historical investigation or to physically interact with the site. The survey could mark the hazard with precision, but identification required a mission designed for historical forensics rather than route clearance. Bridging this critical evidentiary gap required a completely different technological approach and an updated operational framework. The first visual confirmation came in 2001, when an ROV investigation followed the AUV sonar discovery and identified the suspect wreck. A more systematic archaeological mission followed in 2003 using a surface-tethered ROV and precision acoustic positioning to document the site in far greater detail. That later work deployed advanced, surface-tethered robotic vehicles equipped with optical cameras, lighting arrays, sonar, and positioning systems. The operational mandate remained archaeological. Permitted scientific work, including biological experiments and rustical sampling, was limited to understanding site formation and corrosion, while remote operators kept their cameras outside the hull and collected high-resolution imagery and video. These visual missions documented the structural evidence necessary to verify the original surface attack, helping lead to the later formal recognition of the initial naval commander. The next question was what the cameras could actually see. When high-definition cameras illuminated the target, the local geometry set the proof ceiling. The submarine rested upright, but heavy silt swallowed the lower contours, and non-intervention rules barred dredging, water jetting, or intrusive sediment removal. The inspection was therefore limited to steel protruding above the mudline. If the lower keel, pressure vessel bottom, or a failure beneath the main deck held the decisive damage, cameras could not reach it. The exposed architecture had to serve as indirect evidence. Fortunately, the massive elements extending upward into the water column provided an incredible wealth of forensic data. The central command structure, commonly referred to as the conning tower, remained highly visible and fundamentally structurally coherent. As the engineering team maneuvered their robotic camera platforms closely around this elevated section, they documented an extraordinary level of physical preservation. The primary defensive armament, including the 37mm and 20mm anti-aircraft guns, remained in their original mounting positions. The optical targeting stations, external ventilation grates, and vertical access ladders showed no obvious catastrophic blast deformation in the visible midsection, though the wreck still carried the ordinary scars of corrosion, sediment, and isolated damage. Even the 105mm forward deck gun survived just ahead of the command tower, though its heavy lower mount was largely swallowed by settling mud. The aiming gears and long steel barrel of the heavy weapon remained recognizable and broadly intact. This preservation delivered a decisive negative finding. A close catastrophic detonation centered on the command space would likely have deformed the visible tower, casing, and weapons, yet the exposed midsection remained coherent. The survey therefore pushed the search for lethal damage away from the center of the boat. As the remote cameras moved forward, the continuous hull abruptly ended in a jagged void where the bow should have been. Locating the missing section required the operators to widen the search beyond the primary wreck. Following a new path across the ocean floor, the investigation team discovered an independent debris field resting approximately 500 feet away from the initial location. Inside this isolated sector lay the completely severed, mangled forward hull section. The condition of this detached segment presented a drastic contrast to the rest of the surviving steel. The metal here exhibited massive explosive deformation. Heavy external plating was violently twisted and peeled outward, pointing away from the internal centerline of the vessel. This localized explosive shearing was consistent with a catastrophic secondary event, but it was not a complete mechanical confession by itself. A depth charge from PC-566 likely damaged the boat and may have ruptured the pressure hull. As the submarine descended, flooding, pressure, impact forces, and a possible internal explosion of unknown origin combined to produce the final structural failure. The outward bent metal near the forward torpedo loading area suggests a violent internal event, but the exact trigger remains unresolved. The artifact pattern indicates that the submarine likely broke apart during descent, probably relatively close to the seafloor rather than at the surface. Once separated, the main hull and bow section followed different paths through the water column and came to rest roughly 500 feet apart on the canyon floor. Documenting this detached forward wreckage delivered a massive positive knowledge gain for the historical assessment. The separation of the bow, the severe localized forward damage, and the wreck's position near SS Robert E. Lee strongly supported the conclusion that PC-566 had delivered the fatal attack. The original tactical report described a depth charge attack across the enemy boat's path, followed by oil and loss of contact. Decades later, the twisted steel on the seabed aligned with that report far better than with the aircraft engagement more than 100 miles away. By mapping the independent debris field, the optical survey validated the initial naval action without needing to disturb the wreck. However, an absolute boundary prevented the forensic investigation from answering every outstanding question regarding the exact sequence of destruction. A strict non-intervention mandate governed the deep water site, permanently prohibiting any physical entry into the severed structure. The remote cameras could meticulously map the outer dimensions of the mangled steel and hover near the jagged tear, but they could not push their sensitive equipment into the dark, hazardous interior spaces. Attempting to maneuver an underwater vehicle inside the twisted wreckage risked entanglement and violated the fundamental rule of non-disturbance. The team could map the exterior conditions, then carry that uncertainty forward into a limited set of explanations. The operational records and wreck evidence therefore left two cautious possibilities: damage near the torpedo loading area involving a torpedo or related ordnance, or flooding and damage near the battery spaces contributing to a later internal explosion. Without access to the restricted interior, the sequence could not be ranked beyond those alternatives. The shattered bow gave the historical case its closure, even as a new biological threat began advancing on the site. In the year 2010, a massive industrial disaster introduced a severe chemical and biological disruption to the deep water environment. A catastrophic offshore platform failure released tremendous volumes of crude oil directly into the Gulf of Mexico. This event cast a profound risk shadow over the deep ocean. While immediate emergency recovery efforts naturally dominated the surface, a silent and highly aggressive biological reaction began unfolding thousands of feet below. The suspended oil did not simply vanish. Spill residues and oil-associated marine snow moved through the water column, and evidence later showed oil flocculant in sediments around U-166. When that material reached the deep seabed, it altered the local chemical and biological setting around the historical steel. For the microbial communities living on and around the wreck, those residues changed the operating conditions. Researchers describe this as a potential driver of microbiologically influenced corrosion, not as a single simple acid attack. Deep water bacteria and biofilms can change the chemistry at the metal surface, alter oxygen and nutrient exchange, and affect how quickly iron is lost from the structure. What had once appeared to be slow degradation in cold salt water was now being studied as a more dynamic biological and chemical process. By comparing pre-spill imagery with later time series data, marine biologists documented a stark and measurable reality. The visual surveys showed accelerated metal loss at U-166 after the Deepwater Horizon spill, and the surrounding sediments carried evidence of spill residues. The data provided strong evidence of a connection between spill fallout, altered biofilms, and faster deterioration, while still leaving room for other environmental factors such as depth, temperature, nutrients, and local sediment chemistry. The positive knowledge gain was clear. Distant industrial surface spills can alter the preservation curve of deep ocean maritime heritage sites. The deep water environment was no longer acting strictly as a static preservation vault, but as a living system capable of accelerated decay. Despite discovering this aggressive biological attack, investigators and engineers remain bound by the strict jurisdictional and ethical boundaries of the site. The standing war grave protections favor observation, documentation, and carefully authorized science over active salvage or intrusive conservation. No reported management plan has treated the submarine as a candidate for coatings, sacrificial anodes, dredging, or localized remediation. Any such intervention would require formal authorization, technical justification, and careful ethical review. Therefore, the present management condition of the submarine is best described as remote monitoring and limited permitted scientific study rather than physical preservation work. The final legacy of the Deepwater Survey mission is twofold. It restored the combat record and turned the wreck into a long-term environmental witness. The visual evidence from the depths forced the administrative correction that restored the surface commander's report to the permanent naval record. Today, the submarine remains a permanent sovereign war grave and a deep water environmental baseline, slowly deteriorating under Gulf pressure as corrosion, biofilms, and industrial spill effects continue to reshape its steel.